The purpose of creating this video is to give you some additional reference material for Module 2, since Module 2 material is, at least parts A and B of Module 2 are probably the most complex elements of the class, with a lot of nitty-gritty details, a lot of different timing parameters, and just having a resource explaining all of this stuff that you can look back at several times is probably helpful. So Module 2 is all about interfacing with the microcontroller. Okay, so these things do not live alone in the world. They have to be interfaced with external stuff. Okay, so that could be cameras to capture input images. It could be screens to output stuff that's coming from the microcontroller. Pressure sensors, right? These are used commonly in, automobiles or embedded devices that need to read in stuff and then output something. Okay, and so practically all microcontroller systems have to be interfaced with the outside world. Okay, and one particular interface that we can use is an external memory chip, which is what modules A and B focus on. So the outline of module 2 looks like this, and the reason why this lecture is being created in the first place is that both module A and B are probably the most complex interfaces that we end up studying in ECE 362. And so A is going to focus on general bus timing. So how do you time a memory interface? What are the general parameters used? And then part B is the specific multiplex bus extension that exists for the 9S12 part that you guys are going to use in the lab or have used in the lab already. So let's begin with a high-level picture of what it looks like to hook a CPU up to an external memory chip. So you start off with your CPU system and your external memory chip system. CPUs are completely driven by a clock. Okay, this is a bus clock, which means that all the transactions that take place between the CPU and the external memory are going to be based on this clock. It comes from the CPU, generated from somewhere on your microcontroller, and it's going to dictate when the memory should do the stuff the memory needs to do. Right? Memories are simple structures. They can store data, and then you can retrieve that stored data from them. So in all of the preceding examples, one cycle of this clock is going to be the time it takes us to do either one read or one write from memory. And all of the timing parameters we look at are relative to that cycle time. The CPU also outputs a signal that says whether it wants to read or write from the memory. So if we think back to module 1 and writing assembly code, you could think of a read from memory as being a load. So you have to go to the memory chip, grab some value, and then put that back into the CPU by storing it into a register. Also worth noting is that the CPU has to read all of the instructions from the external or from a memory chip as well. Right, so even the bits representing the instructions have to be loaded from memory in some way and stored in the CPU so the CPU can execute those instructions. And you'll look at that when you're doing or have done Lab 5. Writing to memory is modifying the state of your external memory or your internal memory, and that can be thought of the same as a store operation. Now, the data bus is, a bus which is a collection of wires. So on any given clock cycle, there's going to be, in this case, it's general n bits. Typical data buses are 8 bits, 16 bits wide, meaning there's 16 or 8 wires connecting the CPU and the memory chip. And this is where the actual data values get placed. So if you want to write the number 5 to memory, these pins or these bits are, these wires are lit up to represent the binary value 5. Same if you're going to read it from memory. Okay, that's how these are the wires that data transition takes place on. Finally, coming out of the CPU is the address bus. So memory is not just one particular, 8-bit value or 16-bit value. You can store to a whole different number of places. And how do we get at which place you're reading or storing from? You get at it with an address. And so again, that address can have a different number of bits than the data bus potentially. It's simple to think about them as being the same width. And so, the CPU will generate addresses to tell the memory chip where you want to read or write from. Okay, so when we're computing the effective address in our instruction set, like we did in Module 1, that's effective. That is the same address. You can think of that as the same address that's getting put out on these pins to tell the memory where I want to read or write a value to or from. And on the memory chip side, it's going to take in these values, okay, just as a simple input for your address. So it's going to read in whatever address the CPU is telling it wants to operate on. And then the data bus is going to be both an input and an output for the external memory chip. It's an input when the CPU is doing a read, or I'm sorry, it's an input when the CPU is doing a write, because the CPU is going to transition data across this data bus and store it in the memory chip. And it's an output from the memory if the CPU is doing a read, because the memory chip is supplying that data. There's a bit, a single wire, effectively to say whether this chip is turned on or not. It may be the case that you want to completely disable the chip for some reason, and so there's a bit associated with that. And then the real controls for the chip are the output enable bit and the memory, or the write enable bit, which basically say whether the memory should be outputting on the data bus, meaning that this is a read operation, the memory is going to drive the pins on the data bus, or if the memory should be sucking in the values from the data bus because you want it to write to the memory chip. Okay, and so both of these are active low, meaning that when there's 0, we're going to be that particular signal is active. And so it never really makes sense to have these both active at the same time. Effectively, we're only going to look at the output enable bit for reads and the write enable bit for writes. Now, you'll notice that there's missing connections here, right? So I haven't showed you how you actually get at the chip enable bit. So what typically happens is the uppermost bits of your address can go into some kind of decode PLD, programmable logic device, that takes a look at those bits and decides, should I turn on this memory chip based on the address the CPU is looking for? So this is useful in particular if you have a multi-memory chip system. So let's say you've got 2 memory chips, and one of those chips is going to be responsible for all of the lower addresses in your address space, and one of those chips is going to be responsible for all of the upper addresses in your address space. You can figure out which chip the address needs to go to simply by looking at the highest order bit of the address bus, right? If that bit is 1, then it's going to be one of the higher values representable with that address. And if that bit is 0, then it's going to be one of the lower, in the lower half of values representable with that address. And so this little block of logic is going to decode, in our simple example, I said 1 bit, but it might be a couple bits because you have a few memory chips that you're connecting to, and it's going to decide, all right, based on this address, which memory chips are turned on. The other bit of glue logic, as we call it in between, is associated with the read-write bit and the clock signal, and those flow through to drive the output enable and the write enable bit. Effectively transitioning these bits when the CPU has set up the read-write bit in the way that it wants. So when it wants to read something, this bit is going to be high, and when it wants to write something, this bit is going to be low. And then transitioning each of these signals at the appropriate time, which ends up being the falling edge, the rising edge of the clock, to basically tell the memory to start either outputting something or to tell it to start reading in the data that's the CPU is providing, if write enable is what's being done. This list is just the CPU specific parameters. Some are common to both read and writes, like the cycle time, the time to generate the address, time address must be held. Read cycle has some specific timing parameters, setup and hold time in particular. And on the write cycles, there's some timing parameters associated with when the CPU is able to put the data on the bus, which is TDD, how long it's held, and how long it takes for the float delay to take place. So what's most important to keep in mind when we go through all of these exercises is that we're just trying to create a system where the data does not violate setup and hold times. Okay, so setup and hold times are fundamental to circuit operation. And if we're doing a read, which means that the CPU is going to be reading the data from the data bus, we need to make sure that we do not violate the CPU's setup and hold time parameters. Okay, so when we sort of go through the example and piece all these things together, these setup and hold time parameters are the fundamental piece that we're trying to make sure that is not violated with all of this other timing parameter stuff. Parameters for the memory, it doesn't have any common timing parameters. On a read cycle, it's got delays associated with how long the memory needs after each of the input lines stabilize, which is what all the TAA, TCE, TOE timings are. And then we have a little bit of time associated with holding on a read, and then some float delay time on a read as well. Because the memory is going to be providing the data on the data bus, so it's going to have to hold that data for a certain amount of time, and then it takes a little bit of time for it to transition into high impedance state, which is what float delay is talking about. Float delay is the time it takes to get to the high impedance state after the hold time. On a write, the timing that we're trying to not violate is the setup and hold time for the memory. Okay, because the memory is what's going to be consuming the data on a write, because we're going to store something out there. And so TIS and TIH are the fundamental parameters that we cannot violate when we're doing writes. And then we've got parameters associated with write time for the address, chip enable time, and time when the write pulse width occurs. And we'll see how all of these work out when we look at the detailed diagrams. So looking ahead or looking back, depending on when you're watching this, when you look at the 9S12, we have roughly the equivalent signals on the 9S12 that we do on these examples. A little more complicated. We're multiplexing the bus, which makes it a little trickier, but we have the same read-write enable bit. We have E-clock, which is the same as the clock in our simple examples, and then we've got a bunch of pins associated with the bus, which is multiplexed between data and address in the case of the 9S12. And in the simple examples, we assume you have two different buses. So the first example we're going to go through is successive synchronous reads. Okay, so this means that the CPU wants to take data from the memory, it wants to read it in. Successive means that we're assuming that we've got reads back to back, and synchronous is because this whole process is driven by a clock. So the first signal to look at is the clock signal. It's your standard oscillating clock signal where the high time and low times are equal. Okay, simple clock signal, and this is what we would call the bus clock. So the first signal we're going to look at in terms of driving the memory chip is the read-write bit. So the falling edge of the clock triggers the CPU to initiate a read. So why is it initiating a read? Well, because we're looking at successive read cycles. So we know that on the falling edge of the clock, the CPU is going to initiate a read, and the assumption is that on this next falling edge, it's going to initiate another read. Okay, so every clock cycle, it's going to start a new read process. When that clock falls, it takes some amount of time for the bit, this read-write bit, to actually become valid, which is where this green space is. And since this is a read, it means that we want to read something from the memory, so the signal is high. Okay, and this cross-hatched piece here is the time where the signal on the read-write line is not held constant with whatever it was on the last cycle, but it's a time where the value is changing potentially to basically stabilize at the correct value once the signal becomes green. The next signal that we'll look at is the output enable bit. Now remember, the output enable bit is driven by the read-write line as well as the clock signal. And so when the clock fell here, it triggers a transition in the output enable bit. And it took some time for this to happen, and that's because in this simple example, we're assuming that there's some propagation delay. Okay, so the R signal, which is one of the inputs to this gate, is high, and then the clock signal was high, for this period of time, which meant that OE was 0, and then when the clock fell, OE transitioned to be 1. Okay, and so OE was 0 because we were doing a read on the last cycle, and then we're going to do a read on this cycle, but we're going to have to actually transition that OE back down to 0 later on when the clock goes high, based on this logic. And that's just a symptom of the way that this circuitry is set up. The CPU also has to drive the address lines. So, in our simple examples, the time between when the clock falls and when the read-write bit becomes valid is TAD, or timed address generation delay, which is the same as the time between the falling edge of the clock and the address pins becoming stable. And so again, we've got these areas where the signal is not defined, it's not guaranteed to be in any particular state, which is why we have a crosshatch. Why is this crosshatch different than this one? Well, because this is one single bit, and this is actually a bus, which means that this is a bunch of bits. So those bits can be zeros or ones. We don't really care what the value of the address is. We just care when that address is valid. Okay, so all of these signals are single bits, and then this guy is a bus, which is why we've got the double red lines, basically saying that, all of those pins could be some value. We don't care what the value is, we just care about when it's valid. The next signal we look at is the chip enable bit, and so this thing transitions after the address stabilizes. Okay, so if we look at the input to the chip enable bit from the previous slide, we took some bits of the address, we sent them through this address decode PLD, so we had some delay for when chip enable starts changing. So address is stable for this whole region, so chip enable doesn't change. Now the address starts to flip around a little bit. We don't know what the state of the address is because it's transitioning. But the chip enable doesn't see this transition right away. Okay, it is delayed because we're assuming that there's some delay for the signal to get through this logic and show up at the other end. So this little bump is associated with this crosshatch, but it's shifted over by one cell because of the delay. Similarly, when this signal becomes valid in the next time division, then the chip enable bit should become valid, but that again is delayed because it takes it that extra little bit of time to get through the PLD. So this chip enable signal is completely driven by the stability of the address bits, and as soon as those things are stable, there'll be some propagation delay for it to pass through the PLD, and during which time it might be flipping from 1 to 0 because the address had this transition phase. And then once the address is stabilized and you pass through the PLD device, then the CE bit is definitely stabilized. We'll skip this. So the next and the most important piece here is the data line. So this is a read operation, which means that the memory is going to be driving these data pins. And so this first bit of the data line is a result of the read from the previous cycle, and then the real read from memory that's happening on the cycle in question is happening beginning here. So at this point, the memory is outputting the data on the data bus that the CPU wants so it can potentially read it. So how does this happen? How does the memory chip know when it's supposed to drive this data bus? Because this whole thing is really all about when does your data bus become valid. So there are three things that must be true for the memory to output the correct data lines, the correct data values on the data pins. And the first is that the chip is turned on. Okay, so the CE bit is enabled. And so we've shown that that became valid at this particular time division. The second is that the address is valid, which happens here. And then the third is that the output enable bit is on, meaning that the chip is being told that it should output the value stored at this address. So all three of these things became true at different times in this CPU cycle. And when we look at critical path analysis, we start looking at, the last, we take a more detailed look at what timing actually matters most for when this guy starts spitting out your value. But the bottom line is that this, on a read cycle, this thing cannot turn to the green correct value until all three of these things have stabilized, plus some time for the memory to actually do that lookup and drive the pins on the data bus. Remember that this middle line represents a high impedance state, meaning that neither the CPU or the memory chip are driving the data lines. They're basically sitting floating, waiting for somebody to take control of those pins and drive them to good values. So effectively, you can think of it as, all of these things have to be valid first, and then the memory effectively has to take some time to think, to look up your value, and then spit it out on the data bus. Now the real read, the actual read, the latching in of those data bus values happens on the falling edge of the clock. And that's because reads are writing data into the CPU, and the CPU is completely centric on the clock. So that falling edge of the clock means that the CPU latches in the values on the data bus. And so when we're looking at, okay, let's make sure that we don't violate setup and hold times, it's going to be relative to this point where the CPU actually thinks that the read is happening. So let's start putting some of these real values, or not real values, but let's put some labels on some of these timing parameters. Cycle is obvious, right? This is the cycle, the number of nanoseconds that's in the bus cycle. TAD is the address generation delay time, and in this case, it's if these were nanoseconds, this would be 30 nanoseconds, and so that parameter, which is defined for the CPU, says that after the falling edge of the clock, it's going to take this TAD amount of time before the address is valid on the data bus. And then TAH is the address hold time, and that number specifies how long the address is going to be held on the data bus after, how long the address is going to be held, how long the address is going to be held on the address bus after this falling edge of the clock. And again, we're showing this associated with the read-write bit, but the timings for the address line are the same as the timings for the read-write bit on these diagrams. So those are those three parameters. And then, like I said, the most important parameters that we have here are the setup and hold times for the CPU. So the setup time is saying that, for this amount of time before the falling edge of the clock, this signal cannot change and it should have valid data. And so we have to, when we're building these circuits and deciding, what clock frequency you want to use, how fast your memory needs to be, what you really want to make sure is that you do not violate these setup and hold times. So the memory has to be able to supply this data to the CPU by at least this time, or else it's not going to operate properly because you'll violate the setup time, so you may actually read incorrect values. Okay, and nothing works. Now, a tricky bit here is that the memory, so when the memory actually stops outputting, is not triggered off the falling edge of the clock. Remember, the clock signal does not go to the memory chip directly. The only thing the memory has to look at is the output enable bit. And the output enable bit flips after this falling edge of the clock. Right, so remember, there's a little bit of logic dependent on the clock. So your clock fell. Now the output enable bit is able to flip up, but it doesn't happen right away because there is a little bit of this propagation delay. So from the perspective of the memory, this is where the read is being turned off, where you're telling the memory, stop outputting these values on the data bus. We're done. And so for the memory timing parameters, TOH and TOZ, which stand for the output hold time and the output float delay, these are relative to when the memory thinks that it's stopping the output of data, which is not the falling edge of the clock. It's actually when OE is turned to 1. So when you're timing out SRAMs, you need to make sure that this TOH value, plus whatever propagation delay you have, is still within the range of the hold time for the CPU. Because if, your memory, remember, your memory is driving this data bus, and then you're trying to make sure that your CPU setup and hold times are valid. And we need to make sure that the memory chip is going to hold this value for enough time after the falling edge of the clock so that the CPU's hold time is not violated. So in this particular example, everything works out just perfect. So the hold time for the memory is, let's say this is 10 nanoseconds. That taken together with the propagation delay we had on the output enable bit gives us a safe 20 nanoseconds, which turns out to be exactly what the hold time for the CPU was. After the memory's hold time is finished, it will start transitioning the data bus. It will start turning it into the high impedance state because it doesn't know yet whether the next operation is going to be driven by the CPU or by the memory. It doesn't know whether it's a read or a write that's happening next. So it needs to get off of the bus and allow the bus to be driven either by itself or by the CPU, depending on what we want to do on the next cycle. And that amount of time takes TOZ, or output float delay time. And again, these are just parameters associated with memories. An important thing to look at here is the what Professor Meyer has dubbed the FedEx line. Right? Remember, all of this is trying to make sure that we don't violate setup and hold times. And the FedEx line says that you need to have the data ready on the data bus by this FedEx line, or else you're going to violate the setup time for the CPU. Okay, so this line is just drawn, all you have to do is look at the falling edge of the clock, take the setup time for the CPU, and then that gives you your FedEx line. Now, when you're trying to hook memories up to a CPU and not violate its setup time, you need to look at the timing parameters associated with the memory. So each of the inputs to the memory, and the three that we care about on a read are output enable, address, and the chip enable bit. Each of these things, the memory takes some time to actually make sure that it's read in properly. So the CPU has to make sure that the address is set up correctly here, and then it will take the memory TAA time to actually guarantee that it will start outputting the right value on the data bus by then. Same thing with TOE. It gets set up properly here, but then it takes the memory TOE time to make sure that it's effectively read that signal. Same thing with TCE. So in this case, where we've drawn out TOE, TAA, and TCE, they're consuming all of the time between the FedEx line and when each of these respective signals becomes valid. And so this particular diagram represents the maximum values that a memory could have for these values, for each of these timing parameters and still maintain correct operation. So it's confusing because we're actually showing the memory outputting something valid here, but we're, as we sort of go through the next, detailed timing analysis, if the TOE was actually this long for your memory, then you wouldn't have the data being output here. You would actually have the data being output here, and you'd have no read timing margin. And so that brings us to a discussion of what the read timing margin is. So the read timing margin is just the delta between when the data becomes available from the SRAM and when the FedEx line is. So we had a quick clicker question on this. The question was, the green FedEx line for a read refers to the instant that the data absolutely positively has to be there within nanoseconds for the memory read operation to be successful. The FedEx line is determined by the read setup time prior to the end of the bus cycle minus the address generation delay, the bus cycle minus the data generation delay, the read hold time prior to the end of the bus cycle, or none of the above. And if you listen to me in the last 2 minutes, you'll know that the FedEx line is completely determined by the read setup time prior to the end of the bus cycle. Okay, so it's fairly simple to figure out where this FedEx line is supposed to be. Next question is, if the value on the data bus changes before the green FedEx line, what happens? Okay, and so none of the above actually happen. So if you actually read this question, so this example is actually showing the data bus changing before the green FedEx line, and that's actually fine. And that's normal operation because it gives you some read timing margin. Okay, so there's nothing bad that happens effectively by having the data ready earlier. The only potential downside you could see to this would be, you're wasting some time, right? Because as soon as your data is ready, you're effectively just hanging out for all this time waiting for the CPU to do the read. And so if you wanted to be more aggressive on performance, you could technically clock your chip faster. But from a perspective of correct operation, there's nothing wrong with this. There's no negative side effect associated with having this stuff ready early. The next question is, if the value on the data bus changes RTS time after the green FedEx line, what can occur? So the answer is that the wrong value might be read by the processor. So, if you take this green FedEx line and then you add RTS to it, you're definitely going to violate the setup time, right? Because, what this question is saying is that the data is not ready here, but the data is actually ready right here. And, you've by definition violated the setup time for this circuit. And it's most likely that you're going to read the wrong value in the processor. The final question is asking you which time parameter has no effect on the read timing margin. And so just by looking at this diagram, we can see that TOE, TAA, and TZE all affect where the read timing margin is. Maybe not by looking at this diagram, but by what I said. And so the only one that's not included here is TOH, right? This does not affect the read timing margin because that's completely determined by these three signals. So let's take a look at writes. They're a little bit less complicated because the memory doesn't have to reply. The CPU has the data ready beforehand and then just needs to output it on the bus. So the read-write line has similar characteristics to when we're doing a read, except now it's going to be the green portion is when the signal is low because we're doing a write. Write enable bit has similar operation to the output enable bit. It flips its value when the clock falls to be low, and then when the clock goes high, it stabilizes to the correct state after some propagation delay. Address has the same timing characteristics as the read-write line. There's some delay in between when it's ready, and then there's a hold time associated with it on the other side. Chip enable is the exact same flow as we had on the read side. There's a little bit of a delay between when the address stabilizes and when the chip enable stabilizes. And then finally we have the data, which is much different on reads than it is, on reads than it is on writes. And this is because we don't have to wait for the memory to reply. We actually have the data ready in the CPU, and it can put that data on the bus as soon as it's effectively ready to do so. So when we're looking at when the write actually occurs to the memory system, again, remember that the SRAM doesn't look at the clock as an input. So the write is occurring when the write enable bit is flipped to high. Right? Remember that these SRAMs are just simple devices, and when the write enable bit is flipped low, we're effectively telling the memory to read in the values on the data bus and just keep on reading these things in. It's like opening up the floodgates so that the memory can read in the values on the data bus. And then as soon as we turn that bit high, effectively turning write enable off, we're saying, all right, whatever value you've read by this time, we want you to latch that into the memory array, and then we're done. So just to briefly review SRAMs from 270, and this is roughly the structure of any simple SRAM chip that you're going to buy. Just at the front here, you're getting the address as an input. There's a decoder here that decodes that address to decide which rows to turn on, i.e. which of these particular rows of bits you're selecting right now. These are on the select lines. And then the input also has a write enable and a chip select bit that says whether the chip is turned on. Writing is enabled, and output enable is telling you whether it's actually outputting anything. And so when we think about the write operation, you can zoom in on one of these cells, and conceptually you can just think of an SRAM bit as just a D-latch where both the select line and the write line being high mean that the latch is open. Okay, so this in pin is basically one of the wires on the data bus. And when this select and write are asserted, the latch is open, and it's effectively saving the value that's being input on the in pin over to the saved state here on Q. Okay, so when we assert the write enable signal in our timing diagram, that effectively opens up all these latches, and they all start bringing in the data values for whatever is on the data bus right now. And then when we take write enable and turn it off, then it stops bringing in those values. So that's why changing write enable from on to off triggers the end of the write operation. So if we apply our timing numbers to successive synchronous writes instead of successive. No, okay. I like that explanation, but so if we take a look at what happens on successive synchronous writes, the write enable signal, like I said, is asserted for this time period, effectively opening up all those latches, and then as soon as we flip it off here, all those latches close up and the value becomes saved inside the memory. So the timing signals on write operations are the same for the clock. We have the same clock cycle on a read as a write. The read-write bit timing is the same, okay, except instead of being high because we were doing reads, it's going to be low because we're doing a write. And the hold time for the address in the read-write line is also the same as in the write case for the read. Now, the big difference is where the data is coming from. So remember, previously the data came from the SRAM, so we had to wait for the rising edge of the clock cycle for the SRAM to give us the data. When we're doing a write operation, the data is available immediately from the CPU, and he just places the data on the data bus after TDD time. So figuring out when the data bus becomes valid for a write operation is simply just looking at the falling edge of the clock cycle and then counting TDD into the future, and then that's when the data is going to become valid. And remember, like we were saying previously, what we're really trying to do is make sure that the data is held constant during the setup and hold times, and the setup and hold times are associated with the memory chip since we're doing a write. And we can see that, for this particular diagram, at least this setup and hold times are valid. And so we do that timing not from the falling edge of the clock, because remember, the SRAM actually doesn't have the clock as an input. We do it from when the write enable bit becomes high. Okay, because that says this is the end of the write. This is where the write is actually finishing in memory. And we had to make sure that we had an appropriate setup and hold time associated with relative to that switching point. Additionally, we've got some write hold time from the CPU. So the CPU, remember, was putting the data on the data bus after TDD, and it persisted that data all the way until here when the clock edge fell. And so you have a guarantee that the CPU is going to keep that data valid on the bus for the write hold time relative to when the clock edge fell. So since this is a CPU timing parameter, it's relative to the falling edge of the clock and not to this WE bit switching. There's also a float delay, right? So the time it takes the CPU to transition to the high impedance state, so that way somebody else can drive the bus potentially. And that is a timing parameter that takes place immediately after the hold time. So the clock falls, you have the write hold time that the CPU is going to hold the write on the bus, the data lines on the bus valid for, and then it's got some timing period where it's going to transition to float delay, which is TWC, and that's a CPU parameter. Yeah, so this box is basically just saying that TWH, right, it's a CPU parameter, so it's based on clock edges, whereas, TIH and TIS are both SRAM parameters, so it's based on where the SRAM actually thinks that the write is occurring. We can look at the critical timing parameters for the write operation, okay, and so associated with writes, we have TCW, time from chip enable to write happening, TAW, time from address becoming valid to the write happening, and TWP, time from the write enable bit being flipped to the write actually happening, which I think stands for write pulse width. Okay, and so it's a little bit, the naming here is a little bit confusing, but it's calling this the write pulse. And so again, just like in the previous diagram, these are the maximum values that an SRAM can have and still satisfy the timing required. Okay, so if the SRAM has a write pulse width that is half of this size, then that's no problem, because the write pulse is held valid for at least that much time. If the write pulse width is longer, then that's bad, because you're not actually holding it long enough. Same with TAW, right? This is the maximum amount of time that takes. Same with TCW. This is the maximum amount of time that you can possibly have. Now, writes usually aren't on the critical path because reads actually take longer because you have to go to the SRAM and get the data and then wait for the SRAM to put that data on the bus. Another thing to note here is, these timing parameters on, the output enable, the address, and the chip enable determined when the data got placed on the data bus when you were doing a read. But when you're doing a write, the only thing that determines when the data becomes valid is this TDD value. So they're a little bit simpler to look at and analyze. And so this, again, so the FedEx line is similar, right? FedEx line is just at what point does the data absolutely have to be ready to not violate the setup time for the write operation? And then the timing margin is simply the difference between that FedEx line and where the data first becomes valid, which is the clock, the beginning of the clock plus TDD. So quick clicker question. The green FedEx line for a write cycle refers to the instant that the data absolutely positively has to be there within nanoseconds for the memory write operation to be successful, which is what? Is that the write pulse width? Is that the input setup time prior to the end of the bus cycle? Is it the input setup time prior to the negation of the write enable, the input hold time following the negation of the write enable, or none of the above? And as we saw in class, the correct answer is the input setup time prior to the negation of the write enable. Okay, so write enable negation happens here, and then you take that line and you subtract the input setup time, and that gives you the place where your FedEx line occurs. So now we're going to take a look with at reads and writes with some specific timing parameters. We're going to set it up based first completely on a CPU. So we're giving you some real numbers associated with how long the clock period is, some realistic numbers for setup time and hold time, and some realistic numbers for the write data generation hold and float delay times. Okay, and so again, remember, we're setting this up. So we're going to build up the timing diagram based on what the CPU is doing, and then potentially what you want to do when you're designing these things is hook it up to an SRAM such that you don't violate the CPU's timing parameters if you're doing a read. Okay. So before we get into that, there is a note here about glue logic. Okay, so there's basically some stuff in between when the signals change on the CPU and when they're visible on the memory. And for this example that we're going to go through, we're going to assume all of those guys are 10 nanoseconds, but in reality you can figure out much more accurate estimates of glue logic delay. So what is the glue logic? The glue logic is just the stuff in between the CPU and the external memory chip. So the decoding PLD up here and the little gates that we've used on the other side. And so, this matters because when any of the signals, to the left of this thing change, they don't immediately show up over here. They actually have to propagate through these gates first and then show up on the other side. And so this first example we're going through in the notes is going to assume that all of the delays are 10 nanoseconds. So as soon as this signal changes here, doesn't matter what any of this logic is, we're going to assume that 10 nanoseconds later this guy's ready. Same deal with the clock. It's going to change, and then we're going to assume that 10 nanoseconds later either of these two guys are going to be ready. Same thing with this side, so the address is going to change, and then we're going to assume that 10 nanoseconds later the chip enable is going to be affected. In your homework, as all of you hopefully know by now, you didn't just assume that there was a 10 nanosecond delay. We actually gave you an able file to describe a slightly more complex version of this glue logic, and then you figured out what the actual timings on a real PLD would be to estimate what the delay is in those signals being transferred. So there are real numbers now associated with this. So we've got, all the way up between 0 and 200 nanoseconds happening over the course of this 200 nanosecond cycle. We fill in the read-write bit, which is dependent only on the address generation delay, or AD, and the address hold time. Okay, so that was 30 and 20 from the parameters that we were given before. And then we take a look at what happens with output enable. So we're going to assume that it's successive synchronous reads. So at the beginning, output enable is going to be low, and then because it was doing a read operation before, so the read was active, and then it's going to flip. And so output enable is dependent on the clock signal and the read-write bit. And so the clock signal transitioned here to a low state. Then we assume that there was this 10 nanosecond glue logic delay, and then output enable changed. So that's the least interesting part of output enable. So output enable sort of stays where it was for a longish period of time. And then the important part is over here where the clock signal transitions again, and output enable is going to change now to go to a low state, but it has to wait that 10 nanoseconds again because we're assuming that the clock is going to change, and then 10 nanoseconds later output enable is changing to the correct value. And so now it's held stable, and then on the other side the clock changes again, and again you've got that 10 nanosecond delay. So that is the glue logic delay. Address has the same characteristics as read-write for these simple examples. The address generation delay, 30 nanoseconds, and the hold time, 20 nanoseconds. CE is dependent on the address changing. So, the chip was enabled previously, and the address was valid for this, from the previous cycle for this whole period of time. So that was held low. Then the address started to change its state. That changing of the address state flipped the chip enable bit because we're not sure what the address is actually going to do here. And so the address changed. The address changed to be some indeterminate state, which could flip this to 1. You could consider this a crosshatch as well. In all of our diagrams, we assume that this guy flips up to 1. And there's actually this 10 nanosecond delay again until we actually get to the good solid value. So the address changes to the right value here at 30 nanoseconds, and then we've got 10 nanoseconds of delay, and then at 40 nanoseconds this chip enable bit is updated to reflect that change. Same thing on the other side. So the address is valid for this whole time. The address changes to some unknown state here with the crosshatch, but since there's a delay in viewing that on the chip enable, we actually still have a good chip enable signal here for an extra 10 nanoseconds before it starts to flip, reflecting the crosshatch here. So a reminder, this is where CPU reads actually occur, on the falling edge of the clock. And this is the window during which the data actually has to be stable. So we need the data to be quiet and valid during this window relative to where the CPU read is happening. Okay, so all of this was completely based on the CPU and the glue logic that you used. We haven't hooked any SRAM up to this thing yet. This is just CPU based. So we can do the same operation for writes, and so this is a completed diagram for writes. Again, it's very similar. Read-write and address operate in the same way as they did for read. Cycle operated in the same way. Write enable operates in a similar way as output enable. Okay, it's just in a valid state on this side of the half of the clock after some propagation delay. Chip enable operates in a similar way. The only difference is, given just the CPU, we know when the data is going to become valid because the CPU is generating the data because it's a write operation. So it just becomes valid after TDD. And since this is successive synchronous writes, we know that the beginning of this cycle is just going to be the leftover from the last cycle, which is a one-to-one correspondence with this stuff, right? So this 2 white cells and one crosshatch cell here is the two green cells and one crosshatch cell from the previous read cycle. That's why this successive, from the previous write cycle. That's why this successive synchronous write classification is important, because that's what was happening at the beginning of this cycle. Okay, so after TDD time, the data pins are held constant at the correct value. Then the clock flips down, so the CPU is going to, try to start, the timing parameters associated with the CPU coming off of the bus kick in. So we know that the CPU is going to hold the data there for another 30 nanoseconds, and then it's going to take another 10 nanoseconds for it to transition to high impedance. And the write is going to be visible to the SRAM here. Even though we don't have any SRAM timing parameters, we know that the SRAM, all of its timing in terms of when the write occurs, is going to occur from this point. So one exercise, as I sort of mentioned previously, is to match a CPU with an SRAM and make sure that that particular SRAM part is not going to violate any timing parameters on your CPU. And conversely, you're not going to violate any setup and hold times for the SRAM using this particular CPU setup when you're doing a write operation. So SRAMs don't have any parameters that are universal to both reads and writes like the CPU does. They have a bunch of read-specific parameters and a bunch of write-specific parameters, which we talked about previously, that will actually put it in real quantifiable values in these diagrams. And so if you fill in the SRAM read parameters, right? So you've got TAA, which basically occurs from the beginning of when the address becomes valid. So we know the address is valid here. So after TAA time, the SRAM has appropriately read in the address. So it's been set up properly. There's TCE, which is applied from when the chip enable bit becomes valid, and then we just add whatever TCE time there was, which in the case of this SRAM part was 1, 2, 3, 4, 5, 6, 7, 8, 80 nanoseconds, and then TOE, which is applied. You basically look at when the OE signal becomes valid, and then you add TOE. And what's important here and reads is trying to figure out when the SRAM starts spitting the data out to the data bus. Okay, and to figure that out, you have to do a critical path analysis. So you look at all three of these critical input signals to the SRAM, the output enable bit, the address, and the chip enable, and you see which one of these occurs last in time. Okay, so, and it's not just the thing becoming valid, right? So in this simple example, yeah, TOE became valid last in time, and then it also is determining the critical path. But what matters is which of these three things happens last, accounting for how long TOE, TAA, and TCE are. So for example, if TAA had been another 30 nanoseconds longer in this case, it would be determining the critical path. And this brown line, which determines when the data starts spitting out, would actually occur right here. Okay, so you need to actually do this analysis, figure out where all these points are, and then determine which one of these 3 points occurs latest in time, and that determines when the SRAM is going to be outputting. And so then to figure out the timing margin for reads, we first start off from the point where the CPU read occurs, which is on the falling edge of the clock, and then we take a look at what the read setup time is, 30 nanoseconds in this case, and we count backwards so we know that this is the FedEx line. So our margin in this case is going to be 40 nanoseconds because the SRAM started spitting everything out here, and we absolutely had to have the data ready to make sure timing wasn't violated here. On the back side of this clock cycle, we then take a look at what happens. And so the signal is going to be held um, for a given amount of time based on the SRAM. Okay, so there's a hold time that the CPU says you have to hold the data constant for this time. And to make sure that the SRAM doesn't violate this hold time, we look at how long is the SRAM actually holding its value valid for after output enable flips. Okay, so remember, the SRAM is controlled not by the clock, but by output enable. And so output enable goes to one state here, meaning that it's telling the chip that it should stop outputting on the data bus. TOH says how long the SRAM is going to hold that data valid after that event occurs. And then there's a TOZ time, which says how long it takes after that output hold time before you actually achieve float delay, or you actually achieve a floating state. So TOZ is the float delay. Okay, so the actual SRAM gets turned, the SRAM putting its data on the bus starts happening here when OE flips, and again it's offset from the clock cycle because of glue logic delay, and then that starts off the hold time for the SRAM. It holds the data valid for this time, and then after the hold time, the SRAM begins transitioning all these bits to a high impedance state, which takes an additional 10 nanoseconds. And so the hold time is not violated because we've got 10 seconds of glue logic here, and then we've got 10 seconds of hold time, and the CPU hold time was 20 nanoseconds, so everything works as expected. And as I sort of stated earlier, reads usually determine the critical path because they have to do a round trip to operate. So we can do the same thing for writes with this particular example. And we can look at, we don't really have to, when we're doing the read analysis, something to keep in mind here, we sort of looked from when these signals became valid and said, what was the last occurring thing here to determine when the data got output. We don't have to do that for writes. Okay, the data becomes valid after TDD no matter what. And so all we have to make sure for writes is that these minimum times for TWP, TAW, and TCW aren't violated, okay, which is clearly obvious from this diagram. You've got lots of room here. Also important is that the CPU isn't violating the setup and hold time for the SRAM. Okay, so this is where the SRAM write actually occurs. The SRAM has a setup time that it says the data has to be held constant for, which we're clearly satisfying, and then it has a hold time where it has to be held constant after the write is flipped up. And so we can see that the CPU is guaranteeing us that it's going to hold that write data for 30 nanoseconds after the falling edge of the clock, and then the memory doesn't actually turn off the write until 10 seconds after the clock because of the glue logic delay. And then that fits within, then it's got a 20-second hold time. So it says you have to keep the data valid for 20 seconds after the write has been turned off, and that 30 seconds of hold time from the CPU guarantees that. Okay, so this does not violate any timing. And then we've got the write to float delay time, which is 10 nanoseconds in this case. And so this is a CPU parameter. So the CPU is holding the data valid for 30 nanoseconds. That satisfies the hold time for the SRAM. And then we've got 10 nanoseconds where it goes ahead and transitions that data back into the high impedance state for the next write. So we've got a question here. This one was actually broken in class. So I'm going to ask it properly in this online video. So it's talking about a situation where there's a read followed by a write, which is similar to what you guys did on your homework. So the question asks, if the SRAM read float delay, TOZ, okay, so that's this parameter here, exceeds the processor's TDD, which is this parameter here, what might happen? Could bus fighting occur? Could the wrong value be read by the processor? Metastability could occur, all of the above, or none of the above. So I'll give you a second to think about this, since you haven't actually answered this question before, or I don't know, pause the video um, if you want to think about it. But the answer is actually the same answer that we had in class, which is that bus fighting occurs. So why is that? So if you've got a read followed by a write, so let's say that this is your read timing and everything here is the same, except we're going to say that, the question says that TOZ exceeds TDD. So that means that this TOZ parameter is going to be bigger than this TDD parameter. What will happen here when you have a read followed by a write, let's say everything else is the same, so the read timing is satisfied, then you've got this really long TOZ. So, this line is effectively this line on the write cycle. And so that TOZ, which is starting here, 10, 20 nanoseconds after the clock, so it would start, 30 nanoseconds after the clock, start right here. If that value TOZ is longer than this TDD, right, so that means TOZ is going to persist out here somewhere, then you're going to have the SRAM trying to transition the bus to high impedance during these two squares at the same time that the CPU is trying to put its data on these lines. Okay, and that is bus fighting. So we're going to have two actors, the CPU and the SRAM, trying to drive the data bus at the same time, which is going to cause this fighting that is the answer. So let's talk a little bit about timing margin. The precise definition of this thing is the difference between the nominal memory performance required and the performance of actual memory component chosen. So when we draw those FedEx lines, that is the nominal performance. So that is as tight as you can possibly be and actually still not violate any of the timing. So why do you need a margin? Okay, so there's normal variations that happen in process of chips, in the environment the chips are running in. If they're running in a really hot environment or they're heating up because they're being run a lot, it can change the specific constants you're using for those timing parameters. So you can't always rely on every chip that you make being precise to the nanosecond in terms of how long any of these timing parameters are going to be. So to account for that, we basically build a little bit of slack, which we call margin, into the timing for these things. So that way, if the timing changes a little bit, everything still works, no setup and hold times are violated. So a safe margin, just sort of hand wavy, what should you do margin is about 10% of whatever parameter is in question. Okay. And so what happens when there's not enough margin? Well, you read wrong values, okay, potentially. Sometimes when the temperature gets hot or when, the chip isn't exactly as the specs say that it's supposed to be. So the question we had in class was if the normal TCE for a CPU memory interface, the nominal TCE for a CPU memory interface is 50 nanoseconds. The speed of the SRAM that should be utilized in order to provide a 10% read timing margin is what? And so 10% of this obviously is 5 nanoseconds. Most of you said C because, 50 plus 5 is 55. But you want your SRAM to actually be faster to get this margin, not be slower, right? A bigger value for TCE means that the SRAM is slower. It requires more time in between when CE changes and when the data is going to be output. So to make the memory faster, it has to actually go the other way. So a 10% margin would mean that you've got 45 nanoseconds for TCE. So it happens 5 nanoseconds faster than you actually need it to. So we just went through this example, okay, which had a 200 nanosecond bus clock, an 80 nanosecond SRAM. Sometimes, for shorthand, people like to say, how fast is the SRAM? And they'll say 80 nanoseconds. They're referring to usually the TAA and the TCE parameters of the SRAM. Okay, it's one of the longer parameters, and it's what people usually refer to as SRAM time. You don't have to worry about that too much. We'll give you the full specs for any SRAM we actually asked you to hook up, but that's just kind of industry jargon or slang. So if the CPU we specified is used with the SRAM we specified, and we've got this constant glue logic of 10 nanoseconds, we get a read timing margin of 40 nanoseconds and a write timing margin of 100 nanoseconds, and that's the whole example. Another thing we went over was stretch, and so the problem here is let's say that you want to build a chip and it's not going to meet your timing requirements. You're going to violate setup and hold time for some reason. So one solution you can do is just slow the clock down. Okay, you can always make circuits slower. So you could increase the cycle time to give yourself more time so it doesn't violate setup and hold. But this is, not good. You don't want to slow down the bus interface. It slows everything down. So you can capitalize on an observation, which is that the real limiting factor here is the time when the clock is high. So that, that second half of the clock cycle is really where the tightness occurs in all these timing parameters. So instead of just making the clock slower, you could make just the high time slower and then keep the low time the same. So that way you're not wasting unnecessary nanoseconds in the low side when all you really need is more high time. And so this is called cycle stretch. The 9S12 is able to do it. The precise definition of stretch is that you have an extra whole cycle of the clock being held high. So in this simple example, we've got a 20. Let's say you have a 200 nanosecond normal cycle. If you're in a stretch mode, then you're going to use the normal 10 nanoseconds of high time, right? So in the normal cycle, you've got 10 nanoseconds low and 10 nanoseconds high. So you do your normal 10 nanoseconds of high time, and then you spend a whole nother cycle of stretch, so a whole 20 nanoseconds in the high state before finally transitioning to low state. So this is the solution to homework 5, problem 1, I believe it was, problem 1 or problem 2, that basically asks you to take a look at a specific set of timing parameters for a CPU, a specific set of timing parameters for an SRAM, and then examine what happens on a read to write transition. Okay, so all of the previous examples we've gone through, in successive cycles, we've been assuming that, it was a read here and then a read here, and or when we're looking at writes, it had been a write followed by another write. For this example, we're going to look at what happens on a read to write transition. So let's step through how you get to all the different values for each of these little blocks one by one. Okay, so clock signal is obvious. Okay, the clock is given at 100 nanoseconds. So the whole duration of the clock is 100, and then it spends half its time low and half its time high. Straightforward. So let's take a look first at the address line. So you're told here that this is a read happening on the previous cycle. So we're going to assume that this was, valid for the read during the course of this whole previous cycle, because it's the end of a read that worked. Now, here's where we really begin looking at timing parameters where the clock falls. Okay, this is this first cycling question starting at time 0. So there's a little bit of white space here, which indicates that the address line is still held at whatever value it was on the previous clock cycle. And so the question is, all right, how do you know how long this white region is? Well, it's the same as the address hold time that occurs on the read for this read cycle. Okay, so if you're looking just at the numbers here, you first look at when the clock falls, and we're just looking at the address line. So then you look at the hold time, it's 10 nanoseconds. So you know that there's 10 nanoseconds between when the clock falls and when the address starts to go into a state that is potentially unknown. Okay, so this crosshatched region is the unknown time. So then how do you know what happens for 20 nanoseconds? Okay, so fine. So you knew 10 nanoseconds because that was the hold time. Now, what's important here is the time it takes for the CPU to generate the address for the bus, okay, which is TAD. Okay, and so TAD is given by this value in the table, and that's 30 nanoseconds. So from the time that the clock falls to the time that the address is available on the address bus is 30 nanoseconds. And so since we've already consumed 10 nanoseconds of that time with the hold time, the other 20 are going to be associated with the state being unknown, because we basically know that the address is going to be held valid here, and then we know that the address is going to be good, the right address after 30 nanoseconds. So this time in between, 10 and 30 nanoseconds is going to be not known yet. Okay. So now let's go down and take a look at what happens to the chip enable line. So the chip enable line is, remember, if we look back to our original diagram, which you always should kind of have an idea of what that looks like in your head or have it in front of you when you're doing these things. And on your exam, you'll be given the lecture summary notes, so you'll have those pictures so you can visualize what's happening. We can remember that the chip enable bit is dependent completely on the address bus. Okay, and so the address was constant and valid for this entire phase, so the chip enable bit was constant and valid for this entire phase. And then the address was valid again for another 10 nanoseconds into this new cycle, and then it started to change into an indeterminate state. Okay, and so the chip enable is dependent on the address, and so but there's actually a lag. Okay, and for these simple examples, we're assuming that glue logic delay, that propagation delay, is going to be just 10 nanoseconds. Okay, so the address is fine, so the CE is fine for this whole entire frame, 10 nanoseconds into the new cycle. And then CE continues to be fine for an additional 10 nanoseconds, even though the address has started to change and we don't know what state it's going to be in. But that 10 nanoseconds is because of the propagation delay. Okay, so it's still basically whatever we see on the chip enable bus here is reflective of what the address bus looked like 10 nanoseconds ago. So it was stable here, so it's stable here. The chip enable bit flips to a potentially high state here because it's corresponding to this period where the crosshatch occurs for the address, meaning that the address is in an unknown state, so the chip enable bit could be flipped off. And for all of these simple examples, we're assuming that when the address goes to an unknown state, chip enable is going to be off. Okay, you can, if you drew this as a crosshatch, that's also technically valid, but it's maybe simpler just to think about it as turning off. And that stays high for 20 nanoseconds because the address is unknown for 20 nanoseconds. Okay, so this cell corresponds to this cell in the chip enable, and this cell corresponds to this cell in the chip enable. And then finally the address gets itself figured out here, so now it's valid from the CPU. Ignore the yellow stuff for now. And that state is reflected in the chip enable bit 10 nanoseconds later because of the delay. Okay, so the chip enable is always 10 nanoseconds behind address, okay, which is why this is effectively just shifted over. So now let's look at the read-write bit. And so the read-write bit has the same characteristics as the address line in these simple, address data bus systems. And so it's held constant from the previous cycle for this long. It's flipping around for 20 nanoseconds, and then it's going to be valid in the state that it needs to be for a read, and it needs to be a 1 for a read because that's how the bit works. Okay, so then it becomes valid. So this read-write line effectively follows this address line perfectly. Okay, because they're both reflecting what's happening inside of the CPU. Output enable is maybe a little bit trickier. So if we recall what output enable was controlled by, remember it was controlled by a combination of the clock signal, okay, which changes here, and the read-write bit. So the output enable is, let's just forget this region for a second and focus on this first clock transition. So we knew that it was a read in the previous cycle, which means that output enable had to be asserted. Okay, it's active low, so it was low. And then the clock signal switched to down, and that falling edge of the clock will trigger the output enable bit to flip. But again, there's propagation delay, so that happens 10 seconds after the clock flips low, 10 nanoseconds after the clock flips to low. And then the chip is basically turned, the output enable bit is turned off, telling the SRAM that it should stop outputting values on the data bus. Okay, and so then that is high for this period of time. And we can sort of safely think about that as being high because this clock signal is always going to be low. And so the read-write bit can flip around and do all kinds of crazy stuff, and it doesn't matter because as long as the clock is low, the output enable signal is going to be high. If you look back at that logic. Then finally the clock goes to a high state, and then 10 nanoseconds later, so the clock is flipping high here, okay, at this point, and then there's a 10 nanosecond delay, and then the output enable bit is updated to reflect the fact that the write bit is asserted, or I'm sorry, the read bit is asserted. Okay, so then it flips down, effectively telling the memory that it should output something. Write enable, we're looking at that signal even on the read timing, and so you're not writing anything during this entire phase. So this read-write bit is always going to be in the read state for this first section here. So this bit is always just going to be always turned off until we get to the write phase. Now let's take a look at the data bus. So let's ignore the first bit of this for now and start filling out the timing, sort of beginning from 0. So remember, this previous cycle was a read, which means that the SRAM was outputting this data from the last cycle. Okay, and so that data value doesn't immediately begin to change because you have to wait for the SRAM to actually get itself off of the data bus. So the data value is going to be held constant for sure until at least the time that the output enable bit flips, because the output enable is controlling the SRAM. So output enable is turned off here at 10 nanoseconds. And then we have to take a look at how long the SRAM is going to hold that data value for. So if you come over and look at TOH here, that's 0 nanoseconds. So after output enable flips, the data signal is not held for any time. So that means that it no longer becomes valid as soon as output enable goes high. But it's not going to go to a high impedance state, right? So remember the transition phase. So the data is being put on the bus by the SRAM, and here output enable flips high, and then the SRAM potentially holds that value for some time. For this particular part, it's not holding it at all. And then there's some transition while the SRAM attempts to get its signals off of the bus and put it into a floating state, so that way somebody else can potentially drive the bus. Okay, and so the time that takes is 30 nanoseconds. And so this begins at the end of the hold time. Okay, so it'll do its hold time first. That hold time was 0. And then it will begin transitioning to high impedance, which is 30 nanoseconds. Okay, and so we see that 30 nanoseconds takes place here. Okay, so output enable flipped to high, then 30 nanoseconds later, uh, the data bus was transitioned into the correct high impedance state. And in this space in between, the signal is unknown. So now let's take a look at the second half of the read cycle. Okay, so we've sort of set up everything so far on the first half of the read cycle. So what's happening here on the second half? So the clock signal has gone high. And what does that trigger? So the address, it doesn't matter when the clock changes. The address is just going to be output by TAD every time. Chip enable, same thing. It's just going to be triggered off of the address changing. It doesn't matter that the clock is high or low. Read write, it is transitioned based on the clock signal. Oh, I'm sorry, no, the read write bit is not transitioned based on the clock signal. It's just controlled by the CPU. So it doesn't matter that the clock signal goes high. But these two signals, these signals related to the SRAM, are controlled by the clock. Okay, so the clock going high effectively begins the transition of this output enable bit. Okay, so that's what initiates the final phase of the read. Okay, so the first phase, so the lower half of the clock, you've got the CPU setting up the address, you've got whatever happened last time potentially getting off the bus, you've got these bits being set up correctly, and then once the clock flips high, we're going to start toggling these bits that control the SRAM. Okay, because remember they're dependent on the clock signal. So the clock transitions to the high state here at 50 nanoseconds, and then output enable will begin to change. But it doesn't change right away because, again, remember there's a propagation delay, that glue logic delay. So that 10 nanoseconds here is because of the logic delay. And then after that 10 nanoseconds, output enable flips to low, being asserted. And then we know that the SRAM is going to potentially start spitting data out. Okay, so at this point, once output enable flips low, we can see that chip enable is asserted, the address is correct, output enable is asserted. Those are the three things that you've got to have set up before your SRAM will start, and the read bit is obviously set to a read operation. But remember, the SRAM isn't actually reading the read bit. Right? It's not actually an input to the SRAM. The only inputs to the SRAM are the address, the enable, output enable, and write enable. Okay, and all three of these things are set up and stable at this point. So now we have to start taking a look at the SRAM timing parameters, okay, which is what these yellow boxes are. So we see that the address became valid here, and then we have to take into account how slow the SRAM is. Okay, so TAA determines how long the address has to be valid for before you know that you're going to get a good data value out of your SRAM. And it's given as 20 nanoseconds. Okay, so TAA here is 20 nanoseconds. So, basically by this point, we know the address has been properly set up inside of the SRAM. Same thing with TCE. Here it's given as 20 nanoseconds. TCE became stable at this point. So we add another 20 nanoseconds. We know, all right, now TCE is stable here by 60 nanoseconds. And the last timing parameter to actually become valid is the TOE. That happens here at 60 nanoseconds. And then we take a look at how long the SRAM needs for TOE to be set up. And that turned out to be 10 nanoseconds, so we add another 10 nanoseconds onto that timing. Now we take a look at which one of these yellow boxes occurs latest in time. Okay, and so it's clear from this diagram that TOE is the critical timing parameter, and that occurs here at 70 nanoseconds, which determines when the data gets spit out by the SRAM. Okay, so the SRAM begins spitting out data right here, which is why we've got a green box. So now we've got all of these signals, so we've gone through how all of these signals have transitioned during that first and second half of the read phase. Now we have to start analyzing whether that is actually going to meet the timing requirements for the CPU, right? Remember, the CPU is doing the read, so we have to make sure that the CPU setup and hold time parameters are not violated on a read. So remember, everything for the CPU begins at the falling edge of the clock. Okay, so at the falling edge of the clock, that's where we begin our setup and hold times. So we take the setup and hold times for the CPU, which are 20 nanoseconds setup. Okay, and then hold time is 10 nanoseconds. And so we use that 20 nanoseconds of setup to count backwards and determine where our FedEx line is. Recall, this means that the data absolutely 100% has to be ready by this point. Okay, so at 80 nanoseconds in our diagram. And then we know that it's going to be held for an additional 10 on the other side. And with those two pieces of information, with the setup time and with the time that the data actually becomes output, we can calculate what our read timing margin is, and in this case, our read timing margin is 10 nanoseconds. Okay. So now let's take a look at what's happening on the back end of this read cycle. So we mentioned the hold time. That hold time has to be satisfied. So remember, it's the CPU that's taking the data off of that's reading the data from the data bus, and it's the SRAM that's putting the data on there. So we have to figure out if the SRAM is going to properly hold that data on the bus for this time frame. So to figure that out, we have to first understand when the SRAM flips off, and that's determined by output enable. And so again, output enable in this case is transition because the clock falls. Okay, falling of the clock, 10 nanoseconds later, because of glue logic, you've got output enable flipping high. Then we take a look at the hold time for the SRAM. Okay, the hold time for the SRAM is 0. I mean, we already did this when we were analyzing this side. The hold time for our SRAM was 0 nanoseconds. So we know that the data on the data bus is going to be basically held for no additional time after OE flips to high. Then we have to figure out how long it's going to take for the signal to get off of the bus from the SRAM, which is time to high impedance, or TOZ. In this case, for our SRAM, that's 30 nanoseconds, and that begins from whenever the output hold time ends. And since the output hold time is 0, it just begins here, basically from the point output enable flips high. If TOH had been 10 nanoseconds, then this would be, you'd have an additional 10 nanoseconds of data being held constant, and then you'd have this 20 nanoseconds of float delay added on. Okay, which would basically cause fighting in this particular diagram once we get to the right operation. And that's it for, figuring out what happens on the data bus during this operation. So now we transition and we take a look at what's happening on this new cycle where we know that a write is supposed to occur. So let's look at all of our signals again. Clock obviously just keeps oscillating. Address, remember, it has the same characteristics on a read as a write, so it's got the same sort of held for one cycle and then potentially invalid for, held for 10 nanoseconds and then potentially invalid for 20 nanoseconds. CE has the same characteristics because it's just dependent on the address. Read-write has similar characteristics for timing, but since we're doing a write operation, the CPU is going to make this bit go low instead of being high. Okay, but the timing here, the sort of 10 nanoseconds of hold followed by 20 of indeterminate, is the same, except that the value here is now going to be low. Output enable, since so what happens with output enable, when the clock went low, output enable flips up to high, and then that just stays at a high state because even when the clock ends up flipping high here, this bit is down, which means that you're not actually wanting to output anything from the SRAM, so that bit just stays at this constant rate throughout the rest of this equation, or rest of this question. And write enable, so what happens with write enable? So write enable will again look a little bit like output enable did on the read. Remember, it's the input to is the input to the SRAM. And so, this was never used during these cycles because these were all read operations. And then when we got into the write operation, when the clock transitioned to the high state, the fact that this write bit or the read-write bit is low and the clock being in the high state means that the write enable bit will end up being asserted. But it doesn't happen immediately at the falling edge, again, because of glue logic. Okay, and then that signal sort of persists throughout the back half of this cycle, and we'll look what happens on the other side when we get over here. Okay. Now let's take a look at the data bus. So we sort of have transitioned the data bus all the way up to this point. Okay, so the read ended. So the read was basically held. The SRAM flipped up the OE bit for the SRAM got flipped up here. There was no hold time. Then there was this transition to high impedance time. Now we have to figure out when is the data bus going to be used properly for the write. And remember, that is completely dependent on a CPU timing parameter, which was the data delay parameter TDD, which was specified as 40 nanoseconds. And so in this diagram, everything just works out nice and evenly. So as soon as the SRAM got off of the data bus, the CPU got onto the data bus to actually put the valid data on the bus. So recall when we were doing reads, it was a more complex analysis to figure out when the data was valid on this bus. When we're doing writes, it's a very simple analysis. You just need to know what TDD is, and then you can determine when that data value gets spit out. And that is going to persist all the way until the CPU ends up transitioning that value off of the bus, which doesn't happen until the falling edge of the clock cycle here. Okay. So now let's look at what happens on the back half of this clock cycle. So that's sort of the front half, all of these signals up to this point. Now on the back half of this clock cycle, what initiates a change? So the clock goes high. Okay, fine. But remember, the SRAM doesn't actually have to output anything on the data bus now. Your data bus was already valid from the CPU. So the clock going high is going to initiate the SRAM read. And how does it do that? Right, because the SRAM is reading, if it's a write operation, that means that the SRAM is reading it off of the data bus and it's going to store it inside the SRAM. It does it based on the write enable bit. Okay, so the clock transitions to the high state 10 nanoseconds later because of glue logic delay. The write enable bit falls low. Now the SRAM is going to effectively be reading in the values on the data bus. Okay, so the data is valid by this point. You've got the write bit valid. You've got the chip in it, or I'm sorry, yeah, you've got remember, it's not actually reading the SRAM is not actually reading this bit. It's actually just reading, both of these bits. The write enable bit is valid by this point. Chip enable is valid. The address is valid. The data is valid. So by this point, the SRAM is basically sucking in all the values that are on the data bus and storing them to the correct address in the SRAM. And this situation effectively persists. Okay, so ignore the FedEx line for now. So the situation persists until the SRAM is told to stop writing the values, which happens here on the transition of write enable. Okay, so write enable flips to high. Why does it happen at this time? Well, remember, it's just dependent on the clock. The clock fell 10 nanoseconds later. You've got write enable coming high. Okay, ignore the yellow stuff for now. We're not talking about the yellow stuff yet. So that initiated the end of the SRAM where the actual write occurred. So all the timing associated with the SRAM is going to be done from the flipping of this write enable bit. And the timing parameters that we don't want to violate here are the timing parameters for the SRAM. So the input setup time and the input hold time, which were, if we look at these numbers we're being given here, are 20 nanoseconds and 10 nanoseconds. Okay, so 20 nanoseconds before this and 10 nanoseconds after it, we have to make sure that the data does not change. Now remember, it's the CPU actually outputting the data here. So the CPU timing parameters are going to dictate how long that data is held valid for on the bus. So the CPU fell here And then we begin the falling of that CPU tells the CPU that, or the falling of the clock tells the CPU that it needs to get that data off of the bus, and it begins the transition um, right here. Okay, so it begins the transition here when the clock falls, and then the data is going to be held for 20 nanoseconds because the write hold time was specified as 20 nanoseconds. And oh, look at that, it just happens to work out, right? So the data is held valid for 20 nanoseconds after the falling edge of the clock, and then TIH for this SRAM was 10 nanoseconds, and that is applied from write enable being flipped high, which happened 10 nanoseconds after the clock fell. So the 20 nanoseconds of hold time is satisfied by the 10 nanoseconds of propagation delay that we had here, and then the other 10. I'm sorry. The hold time effectively begins here because of the 10 nanoseconds of propagation delay, and then you've got to make sure that it's held for these 10 nanoseconds. And the 20 nanosecond write hold time inside the CPU guarantees that this is not violated. Then we've got a small transition time where the CPU now needs to get off of the data bus, which is the CPU's time to high impedance on a write value, TWZ, which is 10 nanoseconds. So there's this phase where it transitions to finally float, where no one drives the data bus. Now let's take a look at these yellow boxes. Now the purpose of these yellow boxes in the write operation is just to figure out what your write timing margin is. So we take a look at when the SRAM sees the write happen. And so the time for the write pulse is basically the timing that gets applied to the write enable bit. And we can see that write pulse, the minimum write pulse time that we've got here is 10 nanoseconds. So we look at where the write enable bit flipped, and then we count back 10 nanoseconds and say that, okay, the SRAM, that this is satisfied, that there's no problem here with setting up the SRAM. It's definitely valid for at least this much time. Now we take a look at TCW. So is the chip enable bit valid for at least this much time, 20 nanoseconds in this case? And it turns out that it is. Okay, it was valid right here. And then we look at TAW, which says, the address had to be valid for at least this much time, and obviously it is. So what's interesting here, and you should sort of take note of, is that it doesn't really matter for the write timing margin what these three timing parameters are. Okay, because remember, even though in this diagram it looks like, for some reason the FedEx line is occurring, right where these yellow boxes end, that's not actually what you look at to determine the right FedEx line. The right FedEx line is dependent only on the data bus, okay? Just like the read FedEx line. The tricky part with the read is that we didn't know when the SRAM was going to start outputting valid data, so we had to look at all these timing parameters to determine when that was going to be true. For the write, we know that the data is going to be valid as soon as the CPU is able to spit it out, which happens after TDD. So to determine the write timing margin, it's a simpler exercise. All we do is look at when the write occurs, which is when the write enable bit flips high, and then we subtract TIS because that's the input setup time for the SRAM, and that gives you your FedEx line. And then your margin is simply, the difference between that FedEx line and where the TDD point occurs. So this is usually bigger than the read timing margin because reads are slower because you have to go to SRAM and get the value. So you might ask the question, okay, why do I even care about TAW, TCW, and TWP? Generally, you don't really care about these things. You just have to make sure that they are not, that their timing is actually satisfied. So for example, if TCW had been, it's 20 nanoseconds in this case, but if TCW had been, 20, 40, 60, 70, 80 nanoseconds, then this operation wouldn't have worked because we wouldn't have actually completed the right operation in time. Okay, so even though they're not used to determine what the FedEx line is, TCW, TAW, and TWP have to be satisfied or else the write will not complete correctly. And like I said, we usually don't have to worry about these because the reads are much more timing critical than the writes. And so hopefully that's sort of given you an overview of how to solve this homework problem. And this ends, yeah, this actually ends, 1A. So, if you took the time to sort of read, follow this thing through, feel free to make comments or ask questions. Questions are probably most helpful. Comments are fine also. Um, you know, Related to this video, and I'll be taking a look at it and trying to answer those questions as you try and understand the details of this timing diagram. But hopefully that's given you an overview of how you construct these diagrams, when you're on your own and you've got to sort of do it all by yourself. And so again, doing this as practice without me dictating it is useful because then you'll kind of know if you actually know how to do these things.